Silly putty is a visco-elastic fluid. It will flow under a low strain rate and will behave like a solid when the strain rate is large. This means it is a non-Newtonian fluid. A big hype on the internet nowadays is homemade slime. This is made from mixing a solution of PVA with a solution of borax. PVA is short for polyvinyl alcohol, which is a polymer made of ethanol monomers. Borax forms tetrahydroxyborate in water, and this will in turn form hydrogen bonds with the polymer. These crosslinks are what gives the substance its solid-like behavior, and the space between the individual polymers enables the slime to flow when subjected to a force like gravity. This force causes a relatively low strain rate, so it will flow. If the concentration of borax to PVA were too high, the substance would form a solid lump and would not flow at all. When separate blobs of the slime were to come into contact with each other, they would eventually form a single, whole mass. This is because the material is self-healing. The hydrogen bonds between the PVA and borax take time to form. This is why the material eventually snaps when the strain rate increases, because it cannot heal itself in time. The material can be represented by a Maxwell model of a spring and a dashpot connected in series. When the strain rate is low, the dashpot has enough time to compress and the material can flow. When the strain rate is high, only the spring has time to compress and the material will show elastic properties. The elastic properties of the material can be shown by dropping it. When it hits the floor, it will compress and store its kinetic energy and potential energy by deforming. The material will then want to reshape itself to its prior form and release the potential energy, causing it to bounce back, exactly like a spring does. We went out of our way and made our own slime to try and see if it behaves as described in the earlier part of the video. We measured the viscosity of the material with a rheometer. This apparatus puts a strain on the material with a fixed frequency, but with an increasing amplitude. By doing this, we could measure the viscosity as function of the strain rate. In the graph, G' stands for the elastic response and G" for the viscous response of the material. The results show that the viscosity of the material decreases when the strain rate increases. At first sight, one would interpret this as if the material flows more easily when put under a bigger strain rate. This, however, is in contrast to what we discussed earlier. The material snaps or breaks when the strain rate is large enough. What actually happens is that the material breaks up into smaller parts when being measured by the machine, and it has no time to heal when the strain rate is large enough. This makes it easier for the apparatus to displace the material, and the machine interprets this as if the material is flowing more easily. What can be concluded from this is that the viscosity becomes less important to describe the material when the strain rate increases. Instead, it should be treated as an elastic solid. This is in confirmation with what was described earlier in the video.
graden zon, zit in het zand. Looking for a bad bitch, pik in mijn hand. Die in die bikini, interessant. Vakka zwempak, dit is het plan. Ik zeg dingen, je draait je piel voor me. En ik hou het zaakje zilt voor je. Je bent lekker als sloop je billboard.